So here is another video to explain how to actually formulate a good hypothesis and how to do the scientific reasoning for it. So what I would often see is that people write a hypothesis and say you're actually measuring how much time it takes to boil different masses of water. Then people would often write the more water is in the kettle, the longer it takes for it to reach the boiling point. Now that is of course correct, but this is not very precise in terms of the wording. So a better way of writing this would be to say, well, what kind of relationship do I actually get? Is it a linear relationship? Is it a proportional relationship? An inversely proportional relationship? So if I know, and I will show you in a moment how to know, if I know that there's a proportional relationship, then I can say, instead of what I wrote above, there will be a proportional, or better, directly proportional relationship between the mass of water in the kettle and the time it will take it to reach the boiling point. And there's a typo here. There we go. So this can be removed, and this is a very good and precise way of actually formulating your hypothesis. Now let's have a look at how you know whether it's directly proportional or inversely proportional. Let's have a look at the maths, and that also relates to the scientific reasoning that you want to back up your hypothesis. So you know so far that in this case, Q is equal to power times time. The thermal energy, let me make this a bit thinner. Thermal energy is actually equal. This was the thermal energy. This, and that would be in joules. This is the power in watts. And remember, you get this from your kettle. It might say, for example, 2000 to 2400 watts, and then you just go with that middle value. So you would pick 2200 watts, okay? And this is the time in seconds. So this was one of the formulae that you have on the task sheet, and the other formula that is relevant for what I'm doing here is Q equals mc delta T. I think the way it was written on the task sheet was slightly different, rearranged, but this is one way of writing them. So if I combine the two, then I can write PT equals mc delta T. In case you're wondering what I'm doing here, I'm trying to find a formula that actually relates the mass of water in the kettle to the time. So I want to measure the time. Okay, this is my dependent variable, and this is my independent variable. So this goes on the x-axis, and this goes on the y-axis. So I want to have the time written here in the form y equals mx plus b. So the time is my y, therefore I can write t equals, well, to get rid of the p, my power, I need to divide by this whole thing by p. And now I'm writing this in a slightly different manner, so that here is my y value and my x is my mass. So I'm writing that at the very end. So what is confusing, this here is the gradient or the steepness and this is my y-intercept. This is where the line of best fit should go through the y-axis. So you see here that the y-intercept would actually be equal to 0, and my gradient would be, let me pick a different color, my gradient would be this part here. This is my gradient. Okay, I'll get back to you regarding that when we actually discuss the results and what you can do with that and how to find the specific heat capacity from your gradient, which can be useful just to validate your results. Okay, so now I have this equation here, and this equation shows me that I don't have a linear relationship. This would be linear, but this one here is actually directly proportional. Directly proportional means it goes proportional. Directly proportional means it goes through the origin. So if I have my results, I'm expecting this sort of relationship with the time here and the mass, my independent variable, being here on the x-axis. If it was a linear relationship, then the whole thing would look like this, for example, or it could look like that. Any of these would be linear relationships where I have y-intercepts that are actually different to 0. Oops, that was meant to go here. It's a bit tricky to draw on the tablet. Okay, so you have an idea of what the mathematical formula is for this, and so you would just write this in your scientific reasoning. So I would put underneath the hypothesis a brief derivation of this formula, or you might have done that in your scientific background information already. And then you can write just one sentence would actually be enough. As the equation T equals C, I can't write a nice fraction on this device here, C delta T M over P shows, I'll write it like this, the relationship between the time T and the mass of water M is directly proportional. If you haven't done so already, then define what the other symbols stand for. C stands or represents, sounds nicer, represents the specific heat capacity of water. And delta T, the change in temperature. And P, the power of the kettle. There we go. You've defined all of these symbols. You have a mathematical formula to back up your scientific statement, your hypothesis, and you're sorted. And then you can relate to that later on in criterion C when you evaluate your hypothesis and when you describe and interpret your data.